To get a clean read of our spot assay results, it's imperative that we get a clear continuum of growth in our serially diluted spots. For this reason, it's essential to get an accurate number of cells packed into our cell suspension. Each of our spots will be 5 microliters in volume, and we want to fit 1 million cells into our most concentrated spot, 100,000 in the next spot, and so on. So let's figure out how to do this. First, we're going to need 2 fresh cultures, one of our knockout strain of interest and one of the background strain that we've knocked it out of. It's important that these cultures are young and still actively growing, as we want as many of the cells we count to be as viable as possible. We're going to take a colony off our plate with an inoculation loop and emulsify it into a ml of sterile PBS by vortexing. This is going to be way too dense to count without giving us a headache, so we're going to do a quick 1 in 100 dilution of this suspension by pipetting 10 microliters into 990 microliters of PBS. Then we're going to take 10 microliters of this and load it into a hemocytometer. A hemocytometer is a small chamber with an etched grid of fixed size, and this is what we're going to use to count our cells at a 40 times objective. As you can see, the grid is broken up into several quadrants. I'm going to count the number of cells in each grid unit, moving across and down as I go, and ensuring that I don't count the same cells twice. This can get complicated when cells lie on a grid line, so an often used rule of thumb is to only count cells that straddle the right and bottom borders. I'm going to count the number of cells in each of these 4 quadrants and then average that value to maximize the accuracy of my final count. I definitely counted that I have an average of 100 cells per quadrant. I'm going to try and get to a milliliter containing about 40 million cells. To figure out the concentration of cells in my hemocytometer, I'm going to multiply my count by 10,000, as the volume above a single quadrant is 1/10,000th of a mil. So that means I have about 10 to the 6, or 1 million cells per mil. I need more than that, so I'm going to go to my initial suspension we diluted from, which will be 100 times more concentrated than our counted suspension, or 10 to the 8 cells per mil. To get 4 times 10 to the power of 7 cells, we need to get a dilution factor by dividing our starting, 10 to the 8, by our target final concentration, 4 times 10 to the 7. This gives us a dilution factor of 2.5. I need a mil of cells to start with, so I'm going to divide 1 mil by 2.5 and get 0.4 mils, or 400 microliters. So I take 400 microliters of my starting suspension and dilute it to 1 mil with 600 microliters of PBS. Now we've got exactly how many cells we need, but not in the correct volume. So we're going to centrifuge at 12,000 RPM for 3 minutes to concentrate our cells into a pellet. We carefully decant the supernatant, and we resuspend our cells in 200 microliters of PBS. 4 times 10 to the power of 7 cells in 200 microliters gives us 2 times 10 to the power of 8 cells per mil, or 10 to the power of 6 cells in a single spot. I know that's a lot of math, but bear with me. I'm now going to aliquot 200 microliters of PBS into a strip of Eppendorf tubes, one for each of our serial dilution series. I'm going to take 20 microliters from my cell suspension and dilute it in the next tube. Pipette up and down to mix it well, then take another 20 microliters from this tube and dilute it in the next. Because 20 microliters is 1/10 of 200 microliters, the concentration of cells in each tube is decreasing by a factor of 10. Now that I've got my properly diluted cells, I can start carefully spotting 5 microliters from each suspension in order on a plate. It's important to get a side-by-side comparison by pipetting a series from both your mutant and your background strain to see how the absence of our gene of interest affects growth. It's also important to do a stress-free control plate. We'll discuss the reasons for this in class. Good luck, everyone.